All right, let's pick up with this same example. And what we just got done figuring out is the span of these three vectors is exactly the same thing as the span of just these two vectors. And that really 1, 1 is not necessary. So it should not be part of the basis, or at least only two of these are needed for the basis. And if you were thinking ahead, you might have already figured out the key to how we're going to actually do this computationally. Because you might have looked at 1, 1 and said, this one is not linearly independent from the other two. And that's exactly right. Linear independence means that 1, 1 is a combination of these other two. And if it's a combination of these other two, it doesn't need to be a new thing in the span. We can just combine the other two to do what this one does. And that's actually part of the book's definition of vector space. So they basically have two parts to their definition of a basis for a vector space. So they say, suppose you've got some vectors. Those vectors are basis if they're linearly independent. That means you won't have too many. And if their span actually makes the vector space, which basically says don't have too few, right? You still need to be able to get to everything in your vector space. But really, this B being a linearly independent set is what's going to be our key computational tool. And I don't know if you remember how we figured out linear independence. But let me just lay this on you. Pivot columns for a matrix end up being the linearly independent columns for that matrix. So if we are talking about the column space for a matrix, which is the same thing as talking about a span, right? Again, this is exactly the same thing as talking about the column space of 1, 0, 0, 1, 1, 1. Null space will be a little bit different, but column space and span are two of the three types that we're going to look at in this section, and really column space and span, exact same idea. And we'll deal with null space a little later. Okay, so really what we would need to do if we didn't already recognize that 1, 1 was the extraneous solution is we would need to, if it was in this span format, we would need to write it as a vector, or sorry, as a, what am I trying to say? As a matrix. It's Saturday night. It's been snowing all day. My brain's a little bit snowy too. Anyway, we would need to put it in this form. We would then need to row reduce, and look for the pivot columns. Obviously, this one's already row reduced. It's already in reduced echelon form, as a matter of fact. And we can already point out the pivot columns right here and right here. So we know that those would be the only ones that are needed for a column space, basis for a column space, or for this span. So now again, that would tell us that 1, 1 isn't necessary. By the way, a basis for a vector space isn't necessarily unique. And unique means just one. There's not just one possible basis here. If I had put these vectors in, again, not necessarily looking at this version, but looking at this version, if I had chosen to put them into a matrix in a different order, or if they had listed them in a different order up here, I might have been row reducing something that looked more like 1, 1, 1, 0, 0, 1. Now, this one's technically not, it is not, I don't know why I said technically, it's just not in row reduced form, right? There's needs to be a 0 below this 1, so you could add -1 of row 1 to row 2, and you can get 1, 1, 0. Let's see, that would make you 0, -1, 1, And now you can see the two pivots are the first two columns. Okay, there's a pivot position, there's a pivot position. So this one and this one would also work as a basis. And that's true graphically. If you can move in the 1, 0 direction and also in the 1, 1 direction, let me draw a little picture. If you can move in the 1, 0 direction that way, and you can also move in the 1, 1 direction that way. Combining those two can also get you anywhere in two-dimensional space. As long as you have sort of two independent directions to move, you can get everywhere. But really, that's going to be our main tool for finding a basis for a vector space that is either described as a span of some vectors or that is described as a column space. We'll look at some more complex examples that aren't quite so trivial in the next video, and we'll also look at doing a null space example in the next video.